In recent decades, physics has been searching for something no one has ever seen. Not light, not a particle, not radiation, only an effect. We call it dark matter. It is supposed to hold galaxies together, shape the structure of the universe on vast scales, and make up more than 80% of all its mass. But to this day, no one has ever seen it directly. This is the story of the hunter, and what happens when the hunter begins to suspect that maybe the prey doesn't exist at all. It all began with a simple question. When astronomers measured the rotation speeds of galaxies, they discovered something that didn't make sense. Stars far from the galactic center move almost as fast as stars close to it. According to Newton's laws and known physics, those speeds should decrease, but they don't. Based on the amount of matter we can see, galaxies should fly apart. To resolve the contradiction, an additional mass was proposed: invisible. One that emits no light, absorbs no light, but exerts gravity. We didn't discover it. The equations demanded it. That's how the concept of dark matter was born. Since then, science went hunting. The first path was gravitational. Not to see the matter itself, but to see what it does. When we examine stellar motions in galaxies, we see behavior as if far more mass exists than can be explained by stars, gas, and dust. We don't see dark matter. We see stars behaving as if it's there. The same thing happens with light. According to general relativity, light bends in the presence of mass. When light from a distant galaxy passes near a massive object, the image is distorted. Sometimes we see arcs, rings, or multiple images of the same object. But here too, the amount of bending is far greater than visible matter can explain. Again, the solution is the same: a halo of invisible matter. Even the structure of galaxies themselves doesn't work without it. In computer simulations, a universe without dark matter looks very different from the one we observe. With dark matter, the models fit the observations better. But this must be said clearly. This is not a detection. It's a model fit. The next stage of the hunt was bolder. If dark matter exists, maybe it occasionally interacts with us. That's how laboratory hunting began. Huge detectors were built deep underground, in mines and mountains, shielded from cosmic radiation. They are filled with ultra-pure materials and wait for an extremely rare event: a weak interaction between a dark matter particle and a normal atom. The idea is simple. The execution is almost impossible. The interaction should be incredibly weak. The events are rare, and environmental noise is enormous. After decades, countless experiments, and unprecedented technology, there is not a single unambiguous detection. There are hints, there are anomalies, but every promising signal vanishes in the next test. Then came astronomical hunting. If dark matter barely interacts with normal matter, maybe it interacts with itself. In some models, dark matter particles can collide or decay and emit high-energy radiation. So the search moved to the sky, mainly gamma rays and X-rays, from mass-rich regions like galactic centers and galaxy clusters. And here Japan enters the story, not in the way anyone expected. In 2014, a mysterious X-ray emission line was reported at an energy of about 3.5 kilo-electron volts. The line was observed in galaxy clusters and also near the center of the Milky Way. It was presented as a promising dark matter candidate, possibly resulting from the decay of sterile neutrinos, one of the theoretical dark matter candidates. Excitement was high. But then Japanese X-ray telescopes entered the picture, led by the Suzaku satellite and later Hitomi from the Japanese Space Agency. Japanese teams performed much more precise spectral analyses, with higher resolution, and with more detailed plasma models. And the result was uncomfortable. In these analyses, the 3.5 kilo-electron volt line either disappeared completely or could be better explained by known physics: potassium emission lines, hot plasma with non-uniform temperatures, complex intergalactic gas that wasn't properly modeled in the original analyses. In simple terms, what looked like dark matter turned out, most likely, to be ordinary physics that wasn't modeled correctly. And the important point is this: The Japanese researchers didn't say, "Dark matter doesn't exist." They said something far more troubling. The most famous spectral evidence for dark matter is not unambiguous. And when the measurements improve, the signal disappears. And when a hunter fails long enough, he begins to ask whether he's hunting the right thing. This is where the alternatives come in. MOND, Modified Newtonian Dynamics, proposes a change in Newton's laws at very low accelerations. It explains stellar motion in galaxies well, but struggles on cosmic scales. Modified gravity theories, extensions of Einstein's theory, add fields or parameters, trying to explain the discrepancy without new matter. Nonlinear dynamics on galactic scales, gravity may not behave simply when systems are enormous and diffuse. Cumulative effects we still don't fully understand. None of the alternatives has won, but dark matter still hasn't proven itself directly. The hunt continues. The detectors are running, the telescopes are scanning, and the data keeps accumulating. But perhaps the biggest question has already changed. Not, where is dark matter, but, is it really there? Or is it a sign that we still don't understand the rules of the game? One thing is certain, the heart of our galaxy still hides secrets, and we are only at the beginning of understanding how deep they go.